Hi everyone, hello and welcome. So we're thinking about continuing onward with our discussion of exponential expressions and then exponential equations. So the first motivating idea is that, well, in terms of exponential expressions, we can express ideas of doubling and half-life using exponential functions, which gives rise to a wealth of examples that we can do. So by definition, the doubling time of an exponentially growing quantity is the amount of time it takes for the quantity to double. The half-life of the exponentially decaying quantity is the amount of time it takes to halve, right? So how long does it take for our output to double, and how long does it take for our output to be cut in half? That's what we mean by doubling and half-life. So in the context of the mathematical definition, using variables, if q is equal to a times b to the t, if b is bigger than 1 and a is greater than 0, then the amount of time it takes for t to double is called the doubling time. And it's going to be the same regardless of where we're starting. If b is between 0 and 1, so the quantity is decaying, then the amount of time it takes to halve is called the half-life. Now let's go back over a second. What's going on between these two? Here we have doubling time. Here we have the thing growing. Here we have decay. We have the half-life. It's being cut in half. Notice the difference. It's however large b is compared to 1. If b is bigger than 1, then each period we're multiplying something bigger than 1 by a. So it's going to grow. And we're interested in how long it takes to double, or triple or quadruple. Suppose b is something less than 1. Then every period we're multiplying something smaller than 1 by a. So the total amount we've got remaining is going to be shrinking. Okay, so here's an example. Number of people owning the latest smartphone maybe, after t months is given by n of t is equal to 450 times 3 raised to the t divided by 6 power. This is the exponent. All right, so this t divided by 6 is our exponent. This means that we have 3 multiplied against itself, 3 times 3 times 3, a total of t divided by 6 times, which might be fractional. How many people own the phone in 6 months? How many people own it in 20 months? So evaluate this expression for 6 and 420. Stop the video. Go ahead and continue on. So here we're just going to evaluate when t is equal to 6. So we have n of 6 is 450 times 3 raised to the 6 over 6 power. Well, 6 over 6 is 1. So we have 450 times 3, or 1350 people. And then n of 20 is 450 times 3 to the 20 over 6. Well, that's not very nice to look at, but with a calculator you'll find out this is 17,523.332. And then the important thing to observe is, hey look, the number of users has tripled from the initial point of 450 to 1350, which is 6 months later. Well, we knew that, right? Because we started with 450, we multiplied it by 3, that's tripling, right? 450 times 3, that's tripling. How did we justify this? Oh, that's what happens when we have 6 months. Right? 6 over 6 is 1, that's what's necessary to have this simply be the initial a times the base b, tripling. Okay. Turns out actually, in general, we can say the function q is equal to a times b to the t over big T describes a quantity that increases by a factor of b every big T years. So let's interpret these. Let's describe these functions and see what they tell us about the value of the investments we're assuming they describe, where t is measured in years. V is equal to 2,000 times 3 raised to the t over 15 power. V is equal to 3,000 times 4 raised to the t over 40 power. And V is equal to 2,500 times 10 raised to the t over 100 power. Well, let's just use this definition here. Q is equal to a times b raised to the t over t. Okay, so this is our a. This is a here. This is a here. This is b. This is b. This is b. Oops. This is b. Here's our big T, big T, big T. All right, so a times b to the t over big T tells us that the quantity is increasing by a factor of b every big T years. So we're increasing, we're tripling every 15 years. We are quadrupling every 40 years. And then down here, we're increased by a factor of 10 every 100 years. Decreasing by a factor of 10 has a nice name. It's called decimating. We don't have, as far as I know, we don't have a really good name for being scaled up by a power of 10. So here's the interpretations. This is exactly what I said. This investment begins with $2,000 and triples, increases by a factor of 3 every 15 years, right? Increases by a factor of 3 every 15 years. This investment begins with 3,000 and quadruples, increases by a factor of 4 every 40 years. And this investment begins with 2,500. It increases by a factor of 10 every 100 years. Okay. Well, what if we have a minus sign for our exponent, right? What if our exponent is somewhere? What if our exponent is negative? Well, here's a link to what happens with exponential decay. So suppose b, we had exponential decay, a times b to the t, where b is a fraction. Well, remember the link between fractions and negative exponents. That's exactly what's going on here. Alternatively, we can represent exponential decay using a negative sign in the exponent. Here's why. Suppose our example, let q of t equals 4 to the minus t. We're going to show that this is equivalent to exponentially decaying by a factor of 1/4 for every unit increase in t. Here's why. So we have q of t is equal to 4 to the minus t. Well, 4 to the minus t, we can rewrite. Remember our exponent rules. A to the n, in parentheses, to the m is the same as a to the n times m. Right? A to the quantity n times m for the exponent. Well, we can exploit this here. We can think of this as being minus 1 times t, and then why don't we just pull that t outside of the exponent, or outside of the parentheses. So we'll write this as 4 to the minus 1 to the t. Right? If we're going the other way from here to here, we're just going to multiply this by the exponent to bring it inside the parentheses. Here we're going this way in reverse. And then, oh, we know what this is. Right? What's this? 1/4, right? 1/4 to the first. That's this, 1/4, raised to the t power. So this represents exponential decay with a growth factor of 1/4. Why? Well, the quantity is getting multiplied by 1/4 every unit of time. Right? And that's what we were saying. Here's exponential decay is represented by a times b to the t, where b is a fraction. That's exactly what we're getting here by virtue of this example. And the same is true in general. Okay, so here's an example of shifting the exponent. So sometimes it can be useful to express an exponential function in a form that has a constant subtracted from the exponent. This is called shifting the exponent. So here's an example. We have to go through the example to be able to see what's going on and the value of it. So the population of a town was 1,500 people in 2014, increasing at a rate of 2.5% per year. Let's express this population of A in the number of years, T, since 2014, and B, the year, Y. Right, so express the population in terms of number of years since 2014 and in terms of the actual year. And then use this expression to calculate the population in the year 2023. Okay, so how can we do this? Well, all right, so the starting value when t is equal to 0 is 1,500. Well, look, here's how we're getting this. We're actually going in reverse of what I wrote, right? So we know the population of the town was 1,500. This is our starting value. By virtue of the fact that we realize this is where we're starting, we know our exponent is going to be 0 for 1,500. So that helps us build this part. And we know our growth rate is 2.5%. So we have 1.025. Okay, so that's how we can get this. Expression written relative to an exponent of t, the number of years t since 2014. Cool, right? So express this population in terms of number of years t since 2014. This is telling us 2014 is our initial value. That's why this is since 2014, and that's why what this t is sort of intimately tied to the idea that that 2014 is our initial value, and we were talking about years since 2014, right? Going back over this to catch that subtlety, we're starting with 1,500 people in 2014. This is our initial period. So our initial period begins at 1,500, We have our growth factor. That's uncontroversial, right? Uncontroversial, that's just going to be 1.025 raised to the tth power for every year beyond 2014. Okay, cool. Well, that's a nice function. What if we ultimately wanted to figure out a function just for the year, not relative, not tied relative to 2014, but just for the year in general? Well, that's what we're going to have to do on the. That's what I have to do next. So, okay, since 2023 is 9 years after 2014, we have t is equal to 9. Okay, so substituting into our equation, we have f of 9. So 1,500 times 1.025 raised to the 9th power means we have 1.025 multiplied against itself 9 times the initial 500, or 1,500, I can read, gives us 1873.294. So approximately 1873 people in the year 2023. Okay, so this is just using this expression and using the fact that 2023 is 9 years since 2014. We took our initial value to be the population in 2014. We took t to be the years since 2014. This all works. Okay, well, suppose we want to calculate the population, or express the population in terms of just the year, just the absolute year y. So if y is the year, the relationship between y and t, well, t is the years since 2014. I've made a mistake here. This should be y is equal to what? 2014 plus t. So here I am. Yeah, I was one off. I was typing too quick. So this should be y is equal to 2014 plus t. I wrote this correctly down here. All right. So in your notes, and I'll fix this for Canvas, this should be y is equal to 2014 plus t. Right? How do we know this? How do we know that this is the case? Well, if y is the year, the relationship between the actual year and t, which is defined as the number of years since 2014. So this is the relationship between the year and 2014, not 2005, 2014. So if y is 2014, t is 0, because this is supposed to be 2014. Let's use this down here, right? If y is 2023, t is 9. Indeed, when we're thinking about 9 years beyond 2014, we are getting 2023. Okay, so now solving this expression for t, which again, this should be 2014. Solving for t, we have what? We switch these variables and the signs. So we have y minus, right? So we have y minus 2014 is equal to t. Okay, so t is equal to y minus 2014. We now insert this into our exponent. Everything else is the same. Here's our initial period, our initial population, our a. Here's our growth rate. Then we have y minus 2014, because t is equal to y minus 2014. Okay? And then we can use this to calculate the population in 2023. How's that going to work? I think my slide got cut off. You can see these. Sorry about that. You can see this written out. I'll just say it verbally. Suppose we're going to use this to calculate the population in 2023. How is this going to work? Well, we'll substitute in 2023 right here. 2023 minus 2014, that's 9. We know it is from this right here. So then we'd have 1.025 to the 9th power. Hey, that's exactly what we had back here. So it's going to give us the same value. Of course it has to, right? This is just sort of a change of variables. We're thinking of this exponent not in terms of t, we're thinking of it in terms of y. So, of course, when we actually plug in some particular year, since this is taking into consideration that 2014 is our initial period, that's still valid to begin here and have the same growth factor, and it works out as being equivalent. More generally, a shift of t naught years gives us the formula p is equal to p naught times b to the t minus t naught. Here, p naught is the value of p in year t naught. Right? So in the equation we just had, more generally, we had what? We had the population. The population p is equal to 1,500 times b raised to the, well, we used y minus 2014. And what makes this a valid equation relative to the previous one? Well, T naught is the year, and P naught is the initial value in the year T naught. So we had 2014 here, and we had the initial value, or the value in 2014, 1500. Okay, so this form is a little bit like point slope form. Y equals y naught plus m times the quantity x minus x naught for linear functions where y naught is the value of y at x equals x naught. It's a little bit like that form. Okay. All right. So lastly, some examples. Let b equals 500 times 1.071 raised to the t minus 2012. What's going on here? This is telling us that our initial year is 2012. Here's the value of the investment from 2012. So this is, I'm just interpreting this. This is telling me that we invested $5,000 in 2012 at a growth rate of 7.1%. We want to see what's going on here. Here we have B naught is 5,000. Here we have T naught is 2012. And this tells us the investment's value in 2012 was $5,000. And then I added this part, the growth rate is going to be 7.1%, right? Okay, cool. So this is just one example of how to read this relative to what we did back there. Okay, so lastly, we can think about solving exponential equations. So this is kind of fun. Suppose we have a sample of 80 million bacteria that we need to be able to generate from our lab using petri dishes. And these things grow by the growth can be represented by this expression, Q. Our population of bacteria is equal to 5. Our initial value is 5 million. This is in millions, times 2 to the t hours. Well, we want to figure out if this is the growth of our population, if this is the equation that, or if this is the expression that governs the growth of our bacteria population, when is this going to equal 80 million? Well, let's set this equal to 80. Let's divide through by, well, I'll leave the mechanics of solving for a second. We'll divide through by the initial value. Initial value is 5. So go ahead and do that, solve for t. Stop the video. All right, resuming, we'll divide through by the initial value. So 80 million, here's our growth rate of the population. We set it equal to our target we're trying to reach, 80 million. We'll divide through by 5. We'll get 16 is equal to 2 to the t. And then how do we solve this? Well, we can solve this by looking at the algebraic structure, right? 2 raised to the 4th power is 16. Since 16 equals 2 to the 4th, we see t is equal to 4 as a solution to the equation. There's 80 million bacteria after 4 hours. Right, so that's the solution. Here's another example. Suppose a population is given by p is equal to 149 times 2 raised to the 1/9, whole thing raised to the t power. When does the population reach 596? So apply the same principle as here. Take our target, set it equal to the expression governing the growth, and then solve for the variable. Okay, so now resuming, yeah, we're going to set this expression governing the growth of the population equal to our target that we're trying to reach, 596. Divide through by 149. We'll get 2 to the 1/9 raised to the t power. By our exponent rules, we can multiply this by this, so we get t over 9. 2 to the t over 9 is equal to 2 to the 4, or 2 to the 2nd. And just like with the bacteria population, for this to be equal to this, we need the exponents to be equal. T over 9 equals 2. Solving for t, well, it's 18 years. In 18 years, the population will reach 596, assuming this is the expression that governs the dynamics of our population growth. Okay, so we can summarize what we've done here more generally, describing solutions to exponential expressions. So I'll come back to that slide. I actually want to do this first. The more general principle for solving exponential equations, if the base is the same, just set the exponents equal and solve. So for instance, if we have b raised to the u equal to b raised to the v, note the bases are the same, b and b. This is like 2 to the u equals 2 to the v, or 3 to the u equals 3 to the v. We just write bu equals bv. We drop the bases, equate the exponents, and solve. So by that method, here is this. Remember, we had 80 is equal to 5 times 2 to the t. 80 divided by 5, 5 times 2 to the t divided by 5, 16 is equal to 2t. Let's rewrite this 16 as 2 to the 4th. Why? Well, because I want to get something with the same base. and then I just equate the exponents and it just falls out immediately. 4 is equal to t. Okay, so this is true in general. If you have the same bases, you can just equate the exponents to solve your equation. Okay, so suppose we want to be able to think about the solutions without actually solving. We can actually get some mileage from this. So this is kind of good. Even without solving the exponential equation exactly, it's useful to be able to identify the qualitative characteristics of the solution. So for instance, it's good to be able to think whether the solution is going to be positive or negative. So for example, suppose we have 5 times 2 to the t is equal to 3. What can we know about t? Well, here's 5 times this factor equals 3. Wait, we have to get from 5 down to 3. So it's got to be the case that t has a negative solution. Why? Well, 5 is bigger than 3, so this portion right here has to be a fraction. It's got to be less than 1. Okay, because we need to multiply 5 by something to get to 3. Do you know what it is? Well, it's 3/5, right? So if we multiply, if this is 3/5, we'll multiply that by 5 and get to 3. So this tells us 2 to the t is equal to 3/5. Well, so that's difficult to get. At this point, it's difficult to get any closer to t than that, but that's not what we're after here. Here we just want to know if t is positive or negative. Turns out t is negative to be able to make this happen, because we need 2 raised to some negative power so that we are multiplying by something less than 1. 2 to the t has to be less than 1 times 5 to shrink us down to 3. Indeed, we showed 2 to the t has to be 3/5. Turns out 2 raised to some negative exponent gets us to 3/5. Okay. Other things we might be interested in? Well, so positive powers, such as 2 to the second, is going to take us to 4. Even a fractional positive power is going to lead to growth, right? The square root of 2 is 1.4142, which multiplied by our a is going to increase. Right? It's going to increase whatever was our initial value. Right? Positive powers are going to give us this growth term bigger than 1. Negative powers, like 2 to the minus 1, which is equal to 1/2, are going to give us a decay factor, something less than 1. So this is just sort of looking at the algebraic structure, trying to get a feel for what it is that we're dealing with and what sort of bounds we might expect on reasonable solutions. Okay. All right, and lastly, so think about the range of the exponential function. Well, not every exponential equation has a solution. So for instance, provided b is positive, b to the x is bigger than 0 for all x. What does this say? This means that the output value for the exponential function has the same sign as the starting value, a, regardless of the value of x. The output value of the exponential function, f of x equals a times b to the x, has the same sign as the starting value. Whatever is a has the same sign, regardless of the value x. Right? Sine of the output value is equal to the sine of a times the sine of b to the x equals sine of a. Well, provided b is positive, if we're requiring that b is positive, then a negative exponent's not going to change the sign of b, is it? Right? B is positive by assumption, so b to the x is positive. Right? It might be smaller than 1, it might be a decay factor, just like back here. Right? We have a negative exponent. Here's our b to the x. It's still positive. It's smaller than 1. We're going to get decay. But the sign is going to be positive, sign positive. So what determines the sign of the output? The sign of a. Right, the sign of a. So this tells us something about what the range is going to look like.